Hello everyone, I'm Kangjin. I'm very excited to introduce our paper, Characterizing Job Microarchitectural Profiles at Scale, Dataset and Analysis. This is a joint work by Peking University and the Alibaba Group. Here is the outline of this slide. I will introduce the background and motivation in the first two parts. Then I will briefly introduce Dataset, AMTrace, and the fourth part I will give some analysis demos about AMTrace. And the last two parts I will discuss other research opportunities and make a conclusion. Recent years, computing resources are increasing. To improve the resource utilization, most IT providers collocate latency-critical jobs with batch jobs on the same host, called LC batch collocation. Usually, LC jobs are essential critical online services like social network services, email services, and the e-commerce trading system. Batch jobs are usually data computing jobs like Hadoop MapReduce jobs or machine learning training jobs. Under LC batch collocation, resource contention between jobs is a key factor of job performance, especially for microarchitectural resources. It occurs in complex pattern and is difficult to eliminate. Analyzing microarchitectural resource contention between jobs is a prerequisite for understanding and mitigating microarchitectural resource contention. However, the existing datasets have some shortcomings. First, they lack of detailed raw data. For example, they have not provided the number of instructions and cycles, which can be used to estimate workload and CPU frequency. And these two metrics are important for performance analysis. Second, existing datasets only provided per job per host metrics. It is constrained because it cannot determine if two jobs are contending for the same logic CPU or physical cores. Ignoring the placement location relationship between jobs will introduce noise and cause inaccurate analysis. So, there is still lack of high-quality datasets. It is the biggest challenge for the analysis. The first question is the matrix selection. What kind of data do we need? We observed that the modern hosts usually have a complex CPU topology, and the logic CPU or hyperthread is the smallest unit of job CPU usage. And we also observed that one job usually have many pods, and every pod have several containers. Container is the smallest unit of resource management. So to provide a high-quality dataset, we need microarchitecture metrics in per container per logic CPU granularity. Specifically, we provide three metrics: the number of cycles, instructions, and cache miss. These metrics can be calculated for other useful metrics such as CPI, MPI, CPU frequency, and MIPS. The second question is matrix collection. Linux provides a user model tool to read PMU counters called perf, but it has a high overhead in production environment. We implement a low overhead count module called kperf. This figure shows how kperf works. When a stagger switch event occurs on a logic CPU, kperf will be triggered by a kernel hook. Then it reads PMU counters of the CPU and records them in a key-value store. By reading the key-value store periodically, we can get the per container per logic CPU metrics. We deploy kperf in a production-level Alibaba collocation data center. This figure shows the architecture. This data center contains many types of LC jobs and batch jobs. To mitigate the resource contention, we used many resource management policies. First, all batch jobs are encapsulated in a kata virtual machine. Kata virtual machine can provide a strong kernel isolation. Other technologies, like BVT scheduling and noise clean, they provide kernel scheduling isolation. BVT allows LC job to pre-meet batch job CPU. Noise clean technology will stop batch jobs if LC jobs are running on its sibling logic CPU. We also use Intel cache allocation technology to isolate the last level cache of LC jobs and batch jobs. We collect one-day data, then get AMTrace. It has more than 8,000 high-end hosts. They host more than 7,000 of jobs and almost 1 million containers. The data center is running in a high load. The average CPU utilization is 52%. The size of the data is more than 2 terabytes. AMTrace provides per container per logic CPU matrix. The right bottom figure shows a 25-minute data sample of AMTrace. Every pixel means the CPU utilization of one logic CPU at one moment. Every pixel can be decomposed to every job's usage. Based on such fine-grained metrics, we can get multi-level metrics and conduct more analysis. AMTrace provides logic CPU level metrics, so we analyze the logic CPU level resource characteristics. Usually, LC job requests multiple logic CPUs, but how they utilize this logic CPU is still unknown. From AMTrace, we observe that the most significant feature is the uneven CPU usage. The visualization method is shown in the right. We first choose the highest load of a job. By sorting the logic CPU utilizations of the moment, we can get a curve. If the curve is horizontal, it means that the job CPU usage is even. If the curve has a long tail, it means the job CPU usage is uneven. We found that the more CPU a job requests, the CPU usage is more uneven. Many 16 logical CPU jobs usually use only one logic CPU intensively, but other 15 logic CPUs are rarely used. For the uneven jobs, our suggestion is that downscaling the CPU specifications. On the one hand, we can reduce the resource cost. On the other hand, we can provide more resources to other jobs. Previous papers show that job performance can be affected by host-level resource contention. AMTrace provides a more fine-grained matrix, so we can conduct a CPU topology-aware analysis. We conclude 4 collocation types, including same logic CPU, peer logic CPU, same socket, and peer socket. Then we use CPU utilization to quantify the CPU contention and use normalized CPI to quantify the job performance. Higher CPI means worse performance. From this bar chart, we can observe that although many technologies are applied, the performance interference still exists, especially the intra-CPU resource contention, including same logic CPU, peer logic CPU, and the same circuit. When the peer logic CPU's utilization reaches 60%, the job performance will degrade 33%. So we need more efficient microarchitectural resource isolation technologies. AMTrace also provides memory bandwidth and memory latency. In this part, we analyze the relationship between memory bandwidth and memory latency. The left figure has 2 significant features. First, memory bandwidth and memory latency is a non-linear relationship. The second feature is interesting. At the same memory bandwidth, there are 2 memory latency distributions. Through in-depth investigation, we found that the cause of this phenomenon is the memory placement. Some hosts are too dim per channel. They have a lower memory latency, and the memory latency is strongly correlated to job performance. Just as the right figure shows, when the memory latency reaches 50 nanoseconds, the job performance will degrade 40% in average. Hence, our suggestion is keep the memory bandwidth under the inflection point, almost 60% of the max memory bandwidth. AMTrace provides the CPU mode information of jobs, so we analyze the impact of CPU provisioning mode on job performance. CPU set mode means the job will be bundled on several fixed logic CPUs, and the CPU share mode means the job will share the CPU with other jobs. The conventional wisdom is that the CPU set mode will achieve a better performance. In AMTrace, there are 138 jobs that both have CPU set and CPU share instances. We observe that 23 jobs have the better performance in CPU share mode than CPU set mode. We use the heat map to show one job's performance difference between CPU set and CPU share. In the left heat map, the color of pixels means the CPI difference between CPU set and CPU share. If the difference value is positive, it means the CPU set's CPI is bigger than CPU shares. Then it shows in green. The right heat map shows the MPI in the same way. The difference of MPI have the similar pattern with CPI. The figure on the right further demonstrates the relationship between MPI changes and CPI changes. The strong correlation shows the cache performance is a key factor of jobs performance on the different CPU provisioning mode. These observations give us an opportunity to optimize the resource management. We can change some job to CPU share mode to save cost and improve performance. And we can optimize the cache efficiency to improve the CPU share's job performance. There are still other research opportunities. The first is fine-grained root cause analysis. Existing methods are all correlation-based methods, but correlation is not causality. Based on AMTrace, we can propose a reasoning-like method to reason out the interference source based on CPU topology. For example, job A is suffering a microarchitectural interference and its performance is degraded. From per container per logic CPU matrix, we can recognize that a job B, C, D are sharing more resource than job E and F, so job B, C, D is more likely to be the root cause. Another direction is job affinity or anti-affinity rules mining. Now, the rules is like two jobs cannot be deployed on the same host. Based the logic CPU level matrix in AMTrace, we can analyze the logic CPU level job affinity or anti-affinity rules, which will provide more fine-grained resource management policies. Let me make a conclusion. In this paper, we provide a new dataset, AMTrace, which provides per container per logic CPU level matrix. And we provide some preliminary analysis of AMTrace and get some interesting findings, including uneven logic CPU usage, difference of DIMMs placement, relationship between memory bandwidth, memory latency, and job performance. And we also analyze difference of CPU provisioning mode. At the end, we invite At the end, we invite more researchers to explore AMTrace with us. And in the future, we will provide richer and longer microarchitecture data. Now, you can achieve more information of AMTrace on our GitHub project. Thank you.